In this video, we're going to discuss two examples. In the first example, we want to produce 40,000 cubic meters per day with a 50% recovery from seawater. This video is each module can handle 1,000 cubic meters per day with 35% recovery. So with two modules in series, the first module would receive 1,000 cubic meters and produce 350 cubic meters per day, where the second module would receive 650 cubic meters per day, which is obviously less than its stated capacity, and produce 227 cubic meters per day, for a total of 577 cubic meters for the two modules. That would be a recovery of 57%. And in this case, we would need 7 lines with 2 modules in each line for a total of 14 modules. Obviously, we're not utilizing the second module to its capacity. So the alternative in that case would be to have a number of modules in the first group and a reduced number combining the product water or reject water of each module. So in this case, we have 7 modules, first stage modules, and 5 second stage modules. So the total production of the first stage is 2,450 cubic meters, and with a feed of 910 cubic meters into the second stage, each of the second stage modules, that would produce 1,592 cubic meters per day. So the total is slightly over 4,000, and again we get 57% recovery, which is always going to be the case if you have 35% followed by 35%. So in this case, this example would use 12 modules versus 14 modules. So that is an obvious savings of equipment and installation costs. Those are not the only factors, but this is an example of staging, and by staging, reducing the number of modules in the subsequent stages. This is a common practice, and in many cases there may be 3 stages or even 4 stages. Okay, here's just a summary of how you can abbreviate the different number of modules. For a 7x5 array like we had just a second ago, you could show this in this fashion. Otherwise, the diagrams could be very complicated. The math for each single stage 1 module is the same in terms of flow and product, reject and product, and for the second stage as well. Also, for a 3-stage system, you could display it in this manner. Okay, next we're going to have an interesting example of a concentration of maple syrup. Traditionally, maple syrup is produced by taking the sap from the maple tree and boiling it. Kind of a homespun industry of the upper Midwest and more famously in New England. And to solve a problem like this, you have to establish a basis. There's many types of basis. You could do it on the basis of 1 kilogram of syrup, 1 kilogram of sugar, 1 kilogram of sap. There's a lot of ways to approach this. In this case, the person wants to produce 300 kilograms of maple syrup, which is 80% syrup, 80% sugar. So that would be the basis. So the first question, how much sap at 1.5% sugar is required? So since the final syrup is 80% sugar, that would be 240 kilograms of sugar divided by 1.5%. So you need 16,000 kilograms of sap to produce 300 kilograms of final product. Secondly, how much water must be removed? Well, we have 16,000 minus 300. So you got to take out a lot of water, 15,700. In the old days, in the homespun industry days, folks would cut down trees, burn the wood, boil the sap down, and make a little syrup for themselves and a little bit for the country store or whatever. Those days are long gone, but it's still a pretty small industry, and it's a very seasonal industry. For example, now, instead of hanging buckets on the tree taps, people use vacuum pumps and plastic lines, and are able to actually increase the yield per tree substantially, and at the same time reduce the labor quite a bit. So moving along, in the past, it's been interesting to try out a membrane, a very tight membrane like a reverse osmosis membrane. So what's the trade-off between boiling the water and using a membrane? So let's take an example of using a membrane to concentrate from just 1.5% to 2%. That doesn't sound like much. But at 2%, the total amount of liquor, if you want to call it that, is now down to 12,000 kilograms. So with the membrane concentrating from just 1.5% to 2%, we've already eliminated 4,000 kilograms of boiling. So the remaining water to be removed is still substantial. 12,000 minus 300 is 11,700. So by this method, we're going to look at how much water has to be removed at various concentrations. So I'm jumping around here a little. The water removed by the membrane at 2% is nearly 25%. So going through these same steps, you can see by going to 2.5%, 3%, 4%, and 5%, we've eliminated up to 71% of the evaporation required by boiling, and there's virtually none left at 15%. So in reality, there would be some leakage, and there is always some economic trade-off in the calculation such as this. But you can see the point of this is it doesn't take a lot of improvement in the concentration, numerical concentration, to make a substantial impact on the ratio of how much has to be boiled and how much has to be treated by the membrane. So this chart tells you the story starting at 1.5%, and it looks like going up into the neighborhood of 3%, 4%, or 5% would be a really interesting place to take the membrane and greatly reduce the total burden. Of course, this is a typical example calculation, and every application is different. So hope this is interesting for you.